Descartes. If you look at my back wall, my wall of mathematicians, he's over there on the upper right. There he is. Rene Descartes. He's the guy you can thank for this coordinate plane here. We call this the Cartesian Plane, in addition to calling it a coordinate plane, after Rene Descartes. He was a mathematician and a philosopher. Back in the day, those two went together. Both mathematicians and philosophers were a search for truth, right? He was a little bit of a strange dude. He didn't believe in getting up early. Who here doesn't believe in getting up early?
Yeah, well.
Okay, well, that's a lot of people don't believe in getting up early. It's not that he would sleep. He would just lay in bed, and that was his important time to think about things. So he would like think. And he's the guy who he would lay there and he'd think, gee, how do I know I even exist? How do I know I'm not like somebody's bad dream or something? How do I know this? So he had a lot of time in his hand to think about things like this. And he came up with this idea of, let's see, je pense, quand je suis, I think, therefore I am. And he came up with that, saying the ability to be able to think about things is proof of your existence. So that was Rene Descartes. So he was a little bit of a strange guy. But he was also a guy who said numbers are hard to look at. Why can't I just make pictures out of numbers? And he was one of those guys who said, let me think about how to graph. And he came up with this idea of the coordinate plane, also called Cartesian Plane. So that's it. That's who you're going to thank for this, Rene Descartes. So what he did was he took like a flat plane and he put these things on here, these lines. This is an axis and this is an axis. Together they are called axes, right? The plural of axis, axes. So we have one called an x-axis and we have one called a y-axis. So when you put two lines like this, you get 4 pieces. So those are our quadrants. And we number our quadrants, 1, 2, 3, 4. How do we number them? Yeah, we all know this. Look at you guys, right? We put a 1 here, and we work around in the shape of a C for Cartesian graph, right? So this one would be 2, this one would be 3, and this one would be 4. Now notice how I wrote my numbers. These are Roman numbers. You write them in Roman numbers. And when I say you, I mean you. You will write them. If I ask you what quadrant, you have to write it in Roman numbers. That's just how it's done. Okay, yeah, so how does it work? 1 is 1 line. 2 is 2 lines. 3 is 3 lines. Now the Roman number for 5 is a V. So you subtract 1 from V to get 4. So 1, 2, 3, 4, that IV. So counting using Roman numbers. Which is not, that's pretty smart of them. What's the problem with Roman numbers? They don't have 0, right? So it's a primitive number system, but it worked. All we need to count to 4. So in quadrant 1, all the points in here have positive coordinates. So your x's and y's are positive. When you get over to quadrant 2, your x values are negative, but your y values are positive. In quadrant 3, both your x and y values are negative. And in quadrant 4, you've got positive x's and negative y's. Okay, so there we go. So if I have the point -2, 4, which quadrant are we going to be in? Quadrant 2, -2, 4. Okay, and again, written in Roman numbers. So I don't want to do this. If you write this, I'm going to assume you know I want it in Roman numbers. Will you take off for that? Yes. Oh, that's sweet. Okay. And it's alrighty. So what do we got here? We're looking at our Cartesian plane again. We've got some new words. Well, probably some that you know. I think you've heard the word origin. The origin is point 0, 0, smack in the middle, right? That's the origin of a Cartesian plane. Now these words, you may not have heard them, but you know what they are. If I talk about an abscissa, I'm talking about the x value. And if I say ordinate, I'm talking about the y value. Abscissa. Try it. It sounds a little bit like sneezing. No, abscissa. It sounds like a toothache a little bit. No. Abscissa. Ordinate. I can at least sort of see that. I see the word coordinate. Maybe that's how we get that to be the y value. I don't know where this word comes from. Might help to remember alphabetical order, right? X and Y, alphabetical order. Abscissa, ordinate are also in alphabetical order. Help you remember which one is which if I use that word. You probably won't hear me using that word that much, but if you read a math book, they do. So I want you to know what those words are. Okay. Alrighty, so how do they work? And again, I know this is review. Based on what I've seen, you know how to graph. But the horizontal value comes first, and then the vertical value. You always, and I will take off for this, if you're using an ordered pair, they better be in parentheses, right? This is your vertical value, this is your horizontal. If this is a positive value, you move right. If this is a negative value, you move left. If this is positive, you move up. If this is negative, you move down. Starting at 0, 0. Okay, so point A, we start at 0, 0, start at the origin. You go 3 to the left, and then you go up 4. So what is the ordered pair for A? Yeah. Well, -3, right? Because I'm going left. I'm going left, so that's negative, and then up is positive 4. What quadrant? What quadrant is that, Gigi? Quadrant 2. And all the teachers I should tell you about the C. I think they did, right? It's kind of a thing math teachers do.
They never talked about the linear
They never talked about when they Descartes, did they?
and Cartesian.
Cartesian Plane. See, that's why you're here. Learn about the big boy, big girl stuff. Okay, good. Point B, how do I get there? I go 2 units to the right, and then I go 3 units down. So what's the ordered pair in parentheses for point B? Yes, sir. 2, right? So I'm going right, so that's positive. Going down, that's going to be negative. What quadrant is that? Quadrant 4, written in IB, right? Going to use our Roman numbers. Who remembers this? Like, okay, got it. Yo, we've done this. Everybody hasn't done this? A whole row, look at them. None of them have seen this before, ever. Have you guys seen this before? This! You see what? This! Okay, he said, yeah, sure. Alrighty. Okay, I think we're still hitting some points here. So let's see, raise your hand if you know the points, coordinates for C. Alright, find Y. 0, 2, 0, 2. Because I'm not moving left or right, so that's a 0, and I go up to. What quadrant is that in? Yeah? Go ahead. 1, 2, 0. This one? Yeah. No. That's C, right? Yeah.
Quadrant 1 and 2?
No.
Here's the 2.
It's on the
No,
y-axis.
it's on the y-axis. No, it's y-axis. It's on the y-axis.
Y-axis.
What quadrant is y-axis? I mean, that's a quadrant?
Quadrant's a y-axis.
What?
Axis is a
Alright,
y-axis.
there's confusion here. Now, you had great teachers, and they taught you to say, when it's on the line, oh, look, this guy. Great. Okay, here it is. When it's on the line, you're supposed to say y-axis, right? Did they teach you that?
Yeah.
Does that answer the question, what quadrant are you in?
Coordinate.
No.
What quadrant am I in? I'm not in one.
Coordinate. Y-axis.
That's not a quadrant.
On the y-axis.
You are, yes?
No
Did you answer the question?
It's just quadrant y. In quadrant y.
Quadrant Y? There is no quadrant Y. Yeah, 1, 2, 3, and 4. When you have to be in it to be in it. If you're on the line, we don't know which one you mean. Some people say quadrant 1, quadrant 2. I don't know. So it doesn't count. You're not in a quadrant when you're on the line. You're on the line. So that's the y-axis. Yeah, you are on the y-axis. What quadrant are you in? You're not in a quadrant because you're on the y-axis. Okay, how about D? What are the coordinates for that one? 10.
3, 1.
Let's see that. We go to the right 3 and up 1 starting from there. And what quadrant? 1. That was pretty clear, right? Not on the line. How about E? Again, put those parentheses in. Yes, ma'am. Let's see. She says -2 and -3. So let's see. E. If I go 2 to the left and then I go down 3, I shouldn't get there. And what quadrant? Yeah, Roman numbers. I like to just put these in here. My little cheaters, I don't have to think about it. If you're on the line, you're not in a quadrant. You're not anywhere. I mean, you're on the x-axis and the y-axis. Alrighty, what am I up to here? Naming points. What would the ordinate value be? Okay, so now I'm using these new words. The ordinate is another name for the y coordinate, okay? Be for any point on the x-axis. And let me label it. This one's x, This one's y. What's the y value? Zero. Think about it. Any point on here. Are you going up or down? So that's got a y value of 0. And we have a special name for points that are exactly on the x-axis.
X-axis line.
Nope. A point on the x-axis has a special name. Let's see how good those teachers were last year. Yes? Oh, biscuit? What?
What did you say? A biscuit.
Oh, abscissa. The biscuit. No. An abscissa is if you've got a point, 3, -2, that's the abscissa, that's the ordinate. That's what those words are. What's it called if it lives here? Here I am. We don't know. Oh, something new to learn today.
Yes, sir.
Ready? Ready for it? Everybody know where to write it down?
Yeah.
Okay. It's called an x-intercept. Oh!
That's fine.
Yes, intercept. It's football. X-intercept. Okay, let's try this one now. See if you can catch on here. What would the abscissa be? Okay, an abscissa is another name for the x-coordinate. For any point on the y-axis. What's the x value then?
The Y.
What is the x value? What is the x value for any point on the y-axis? 0. Because I'm not going left or right. I'm just staying there and then I just go up and down. Points on the y-axis are called y-intercepts. Okay, you guys are getting it. So we have to know these words, and I'm going to use them a lot. And in algebra from here on in, you're going to hear those words a lot. X-intercepts and y-intercepts. Okay. All right, plotting points. So, how do you plot points? You begin at the origin, so you start here. So you move left if your x value is negative, you move right if it's positive, and move up if the ordinate is positive, move down if it's negative. So we're going to plot some points here. So I'm going to have somebody go up to the board for me. They're going to go plot that point A. Let's see. Well, somebody's hand is not up. Oh,
Okay.
what?
Call him.
Pick me.
You're volunteering out of this one. Peters, go ahead, get up there. Go plot point A. Let's do it. And there's a depends right there. And talk while you're the teacher now. Tell me what you're doing.
Oh, okay. The first one.
Everybody else is quiet and listening.
Negative abscissa. 5. So I move 2 spots to the left, and then I move 5 spots up, and go over here.
Label your point, right?
Yep.
There it is, point A. Beautiful. What quadrant?
And in quadrant 2.
Okay, so label that for me also. Not so easy, is it, then, Ken? No. We should give you a prize, Mrs. Grieser. Thank you.
Beautiful.
I have a question for you.
What?
Why do you move over 2 spaces to the left?
Because, yeah, you got a question. Why is that, Peach? Why'd you go to the
Can you
left?
repeat that question, please?
Oh.
No. Why do you move over 2 spaces to the left? Because it's negative 2 and positive is to the right and negative is to the left.
Well, you didn't tell us that.
Negative is
You just
He
said go
did, he did. He actually did a beautiful job. We may have to have Cole go next. All right,
Yeah,
Cole.
Cole.
Awesome.
Can I go next?
No, Cole's going next.
I'm gonna go
Yeah,
next.
get up there.
And you'll be expecting a question from me,
Can I
okay?
get that?
Don't worry, nobody will give you a hard time, Cole.
Yes, he was.
Let's see if he explains it.
So, it's 3. I'm positive, so you go over 2 spaces right. 2
3.
Three spaces,
sorry,
Cole.
3. And then you go 2. Can I erase that?
What can you, how are you gonna fix that? Go ahead, fix it. Go.
You're the teacher, do it.
You're the teacher.
Yeah, teacher.
Wow,
Oh,
you're hostile. See what I have to go on?
What are you doing? Quadrant 4.
Yeah.
Press down on it.
Harder.
Press this.
Oh, there we go. Oh my god.
Hey, don't say God's name with
Oh
anything.
god, he's
It's on the clicker. Let me fix it. Here we go.
Alright, teacher.
Maybe use the board
have a question.
Here we go again. Right? Go ahead.
Question.
Well, you're more.
How come that's quadrant 4?
Because you go in a C motion. So 1, 2, 3,
Can you draw it C, please?
I don't even think.
And what is the name of the C?
Whoa.
He's a wizard. Thank you, Cole. Thank you, Cole.
Can I go?
All right, so that's okay, Cole. It's not as easy as it looks, is it?
Big die.
It was easier than other classes.
Pen doesn't work.
You know what? Pick a girl. All right. Okay.
I'm a
Right
girl.
there.
I'm a girl.
Represent.
Big Schroeder. Danny.
Represent.
And then the last one is P, and it's -4 to 0. So you're going to go to the left, -4, because you know that was 100. So you go -4, and then it says 0 to the right, and you then go up and
No, I
Take that point for me.
I have
See
a
there?
legit question.
And then Claire, what quadrant? She did a beautiful job. What quadrant?
quadrant.
Oh, no quadrant, right? She did a quadrant. None. Right, none.
What is it?
She said go positive to the left.
That's what she meant.
Yeah.
No, she said positive, so that way.
I have a question. I have a question.
It's name.
Wait, I have a question.
All right, hang on.
What's the name of the guy that made the graph?
Jesus.
Testing memory. I
I actually don't even remember.
Claire, you answer that question. See that guy in the upper right corner? Go find it. There he's in the back. Go find it for us.
It's your name.
Upper right. Very handsome guy up there.
MJ.
Ladies and gentlemen.
Rene Descartes.
Rene Descartes. Answer. Thank
You
you.
need to work on your
Okay.
blank.
Ladies and gentlemen. So you may have heard about this last year, have you? Relations and functions. You know anything about this? Yes. All right, so ladies and gentlemen, I need you quiet. A relation, when we talk about mathematics and we talk about a relation, we're talking about a set of ordered pairs. What's a set? Set, curly brackets represent things inside a set. They can be numbers, they can be colors, they can be just about anything. It's like having a bag full of them. So if I have a set of ordered pairs, that means I've got a bunch of ordered pairs. And they give us some values, and I'm just making up numbers here. So I have just given a set here. Okay? So a relation is when you have a set of these. A function is when you have a relation. So you have a relation, but every input has one and only one output. This abbreviation, OAOO, stands for one and only one. What in the world does that mean? What? What does that mean? So we're going to look at that. I want to go over a little bit more vocabulary. So if you have a relation, the set of inputs has a special name. Do we know what that special name is? Do you? What is that?
Carter, you know it's
Starts with D.
a biscuit.
Not biscuit. What is it?
It's supposed to be an E.
It's on your paper.
Quiet. Yes, ma'am? Domain. Oh, is it on the paper? How about that? And then the set of outputs. So my inputs are like you put in an X, your output is to get a Y. What's that called, Matthew? The range. Please don't confuse the range when we're talking about relations and functions with the word range when we're in statistics, right? They're not the same thing. Range in statistics is how far apart the numbers are, the biggest minus the smallest. When we're talking about range for relations and functions, we're talking about output values. Okay, different things. Have we heard these words before?
Yes.
Good. Somebody else. All right, so when is a relation a function? When every input has one and only one output. Now, what does that actually mean? Let's look at the following relations and decide if they are functions or not. So is it a relation? First of all, these little curly brackets means you have a set. These are ordered pairs. You have a set of ordered pairs, so you have a relation. Now, does every input, now inputs are these things. You put in this number, turn some crank somewhere, and this number comes out. So does every input have a unique output?
Yes.
Yes. That makes this a function. Right? Because every input has one and only one output. Let's look at this relation, this set of ordered pairs. Is this one a function? Does every input, here's my inputs, do they have the same output all the time? No? What's the problem? So here's input 1, and here it has output 2. Here's input 1, here it has output 5. So 1 has more than one output. This is not a function. Hang on. Little rule. Now how about this one? Here's my inputs. And then here are my outputs. So does every input have one and only one output?
No.
Yes.
I heard yes, I heard no.
No. Input is X.
Well, why do you say no?
Because all of the second root of each order pairs two.
We see a lot of twos coming out. So we see a lot of the same output, right? Let's go back to my definition. It says every input has one and only one output. Not every output has one and only one input. What's the difference? So this input 1, think of the Coke machine. Right? You ever see the soda machine?
Yeah.
When you push the button that says Coke, what do you expect to come out every single time? Coke. Would it be surprising if root beer came out?
Yes.
Would my Coke machine, my soda machine be functioning correctly if I pressed the Coke button and a root beer came out? No. Okay, now can I have 2 buttons that will give me Coke? Yeah. But every time I press those buttons, I want to have Coke come out. So what it says is, sure, you can get the same output in different ways. But if I press 1, only 2 can come out. Is there any other representation of 1 here? No. Here there is. Sometimes you press your button, the Coke comes out, and sometimes you press the button, a root beer comes out.
No.
Okay? Now when you go down here, every time I press this button, Coke comes out. Now if there's a set of buttons on my machine, I press this one, I also get Coke. I press this one, I get Coke. I press this one, I get Coke. So there's 4 ways for me to get Coke, but this button will only give me that value. Does that make any sense?
Yes.
At all?
Yeah.
No? Well, it's saying an input has one and only one output says whenever you see a 1, the only output you can have is 2. You see 1 ever again? No. Now if I were to add this 1 and a 7, if I were to put this into my set, is it a function anymore?
No.
Because now I'm pressing a 1, I'm getting a 2. Sometimes you press 1 and a 7 pops out. That's not a function. Yeah.
So if the domain has the same one, set is the same.
Yeah, I mean, essentially, what are you actually doing? Well, I'm looking to see, do I see any repeating x values? And if I see a repeating x value, that's bad. Yes, but if you understand why, it'd be much easier. I like the image of the Coke machine. That helps me remember it. Why is this a useful thing for some things to be functions? Why do we even have to worry about it? Are you a bad relation if you're not a function? No. Well, why might it be important? Yeah. Well, yeah, we can graph relations too, right? Can I graph this one? Sure. So yeah, but they are graphable. That is true. I like to think of maybe a real life example. When would it be great to know that a certain input's always going to get me a certain output? Besides a Coke machine, right? I want to know. I press the Coke button. Yeah.
Like if you order something, then you're supposed to get the item. Like if you order like shoes and you get instead like a car.
Tennis racket.
Or
Yeah.
tennis
Yeah.
racket or something like that,
Right.
then you're
Okay, so maybe using an online catalog, you press that button, right? You want that thing you ordered to come, not something else. Right? Gasoline, what do you mean?
like if you put in
variety of gasoline. You ever pump gas? Anybody ever pump gas for their folks? They look, yeah, yeah. There's like different things you push. There's like the regular and some cars only take like special gas. Does your car only take special gas?
Yeah.
You press that wrong button and you put the wrong gas in the car, what's gonna happen? Bad things, right? It's not good for your car. So you wanna be sure when you press that premium button, you're getting premium gas. That's a function. You are assured with this input, you get a special output. I think a medication as well, let's say, you know, a medication is based on weight or something. So if you say, okay, here's this baby, it's thick, and it weighs 15 pounds, and so they may have a calculator that says if it's 15 pounds, give it so much medication. Do you want to get different numbers?
No.
I mean, you want to have a consistent, reliable amount. So functions are actually important in certain applications. So that's why we spend so much time. Is it a function? Is it not a function? So every input has one and only one output. You don't have to worry about the outputs. It doesn't say each output has only one input. There can be multiple ways to get to an output, but each input must be unique. A 1 will always map to a 2 and nothing else. All right? So relations and functions. So let's decide here. Now this is called a mapping diagram. It's another way of representing ordered pairs, a set of ordered pairs. So they write it this way. We can actually write these as ordered pairs if we wanted. Input, output. So there is one way, right? Input, output. Input, output. And the last one. So I can write this as a set of pairs. It's just another way to look at it. Now looking at this, it is a relation, it is a set of ordered pairs, but is it a function? No, why not?
Because 0 has 2 different outputs.
Because 0 has 2 different outputs. That reason he gave was excellent. I hope everybody was listening to that. Because you need to tell me why is it a function or why isn't it a function. He said 0 has 2 outputs. There is an input with more than one output, so it is not a function. The way he said it was perfect. Not a function. Right? If you know where we are, if you want to write some of these words down, his reason was excellent. Because 0 has 2 outputs. Perfect.
You have to write 0, 2, 0, 3 last one.
You don't have to, but I just wanted to show you, I wanted to prove to you, this is a relation, even though it doesn't look like one maybe at first. You can look at this and you're noticing, look how 0 points to 2 different things. So I can tell right away, this is not a function. It is a relation though. We have these relation tables. This is another way of representing ordered pairs. Again, that's 0, 0. Like this is how we interpret this table. Is this a function?
Yeah.
Yes.
Yes. Why?
Because
Why?
Because none of the inputs have the same. I mean, none of the. There's no 2 outputs.
Here's the words. You're right. I know what you're trying to say. Here's the words. Every input has one and only one output. And you can use that abbreviation. This says it. Every input has one and only one output. 0 only maps to 0. It doesn't map to anything else. 1 only maps to 2, not to anything else. Okay? Is this a function? Now I'm looking at a
No.
graph. Now, is a graph a set of ordered pairs? Yeah, I mean, think about it. Like, here's one at 0, 0. I've got, it looks like a 1, and it's hard to see what that is. Maybe that's 1, 1. And I've got a point down here. That looks like maybe it's 1, negative 1. I got 1 and a half. So, you know, I got lots of different points here. So it is, now how many points are on this particular relation? How long would I be here writing points down? How about forever? Would I be here forever if I wanted to write every single point? Yes. Why am I going to be here forever writing all the points down? Well, yeah, this is what we call it. It keeps going. I like that. So when you look at the x value for each of these y values, so yeah, I can see 1, 2, 3, 4, right? They have y values. How about a half? How about a quarter? Can I keep like, how many different x values are there? There's an infinite number in between these two values. There's an infinite number of points here. So I can't really say what all the points are, but I can see them. And so is this a function? It is a relation. It is a set of ordered. Why not?
Because the input will have 2 outputs.
Okay, we have some input. inputs with more than one output, right? So for example, input 1 has more than one output. So for this one, you can say no, because you want these words, so you want to write this down. There are inputs with more than one output. Okay, those are the words we want to do. We want to explain why. Nope, you're doing. Ooh, what do you mean, what if it was negative? So negative 1 and 1, so if I was over here, and we're going to have something here. Is that a function? Negative 1 maps up here, negative 1 maps down there. This is not a function either, because negative 1 maps to more than one value. Now, you may have heard about this vertical line test or the pencil test. Anybody ever heard this thing?
Yeah.
Oh, you may have heard of it a little bit?
Yeah.
And so what you do is you're supposed to take this pencil, I don't know if this thing moves, I don't know how good I was at grading this. What's up, look, hey, look at that. So, and you're supposed to, ooh, let's see, now what, how does this work, this vertical line test? How does that work?
So you put a line here and keep it straight.
It is straight, right? My pencil's straight. So what do you mean? What am I looking for?
If there's anything that is the same line.
Ryan, what am I looking for when I'm doing this?
See if it touches two,
I'm touching 2 points at the same time. So as I cross over this line here, am I ever touching more than 1 point at a time on the line?
And it's not a function.
Well, it is a function, right? If I'm only touching 1 point, it's a function. Isn't that how the vertical line test works?
Yeah.
This pencil test thing? Like this one, I don't know. Oh, look, I'm touching more than 1 point. Is this a function? No. Oh, wow, look at that thing. Is this a function?
Yeah.
No.
Yes, it does.
No.
Because it doesn't touch 2 points at one time.
Doesn't touch 2 points. Now this one is not straight up and down. The basic idea is if you're straight up and down, are you touching more than 1 point? So this one, function, yes. Function, no. Function, yes. Now again, why? You know what's the wrong answer to this question? The pencil test. Does that explain why it's a function or not a function? No. What is the pencil test doing? What the pencil test does is it says, if you're at an x, is there more than one y? If you're at an x, is there more than one y? Now in this case, the answer is yes. If you're over here at an x, is there more than one y? No, there's only one y. Is there more than one y? No, there's only one y. Basically helping you see. You could even just do this and see that there's only one y for every x. This one, I can see there's more. What if I have a function and it looks like this? Or I'm sorry, a relation. Is this relation a function? No. And if I need really my pencil, I can just kind of see. If you were to put lines through here, look at this. This x has all these different y values. It's not a function. So you can use the pencil test. Nothing wrong with using the pencil test. But is that why something's a function or not a function? No. It's a function if every input has one and only one output, and it's not a function if that isn't true. If there are inputs with more than one output. Yes or no?
Yes.
Yes. What? It's gone. Okay. All right. So it's a tool, but it's not a reason. All right. Graphing. Graphic function. Function rules relate one variable to another. So if you have an input, you have some rule, you kept turning the crank, and then out pops your output based on this function rule. So the independent variable, the input variable is in the independent, and the output is the dependent. In science, have you been talking about independent and dependent variables at all?
Yeah, last week.
Last year? What does it mean? And this year, and every year, pretty much. What does it mean? What does it mean?
independent variables can be changed.
Okay, so you change the independent variable? Yeah?
The independent variable is what you're changing, and the dependent variable is
What gets affected.
What changes? A very, yeah, okay. Depends on the independent, it does. A very typical independent is time, right? Is time always independent? You start to watch, maybe, and maybe you're measuring how long it takes for something to roll down the track? No? You don't do that?
Yeah, I
Yeah,
know.
I do that. That's a typical independent because time changes. How much control do you have over time? Not a whole lot. It will change, and then things may depend on what time it is. So when you're graphing things, the example I have here is time and distance. So maybe you are timing how far something rolls, based on time. Independents are your inputs. So there's your independent. It always goes as your x-axis, and your dependent, it depends on it. How far it goes depends on how long it's rolling, right? So it depends on that. That's always going to be your y variable, okay? So which variable is independent here? The time. That's independent. It's always what's on your x-axis. And then your dependent is always your y value, your output. So in this case, it's going to be distance. So this is in science and in math, they mean the exact same thing. So we're giving it kind of a more mathematical way of looking at it, but they do mean the exact same thing there. So questions on dependent, independent, that kind of stuff? Alrighty. This next thing, it used to be, when you walked into the Algebra 1 room, everybody knew how to graph using a function table. I know they teach it in Math 7, so if you're in 8th grade, you might have seen this. But I don't know if they teach it in Math 6A.
What?
So, using a table to graph.
Yeah.
Yeah?
Yeah, we did watch it.
Okay. Because every year people come and say, we've never seen this before ever. So we're going to pretend we've never seen it before ever. What this is, it's what we call function table. Kind of like a little fun little word for it. And so what you do is you make a little table. Sometimes it's called a T table because you can make it just by making a T. And there's X and there's Y. And so what you do is you enter domain values. Now what does that mean again, domain? What's domain? Set of inputs. So domain is a set, so I got my curly brackets, of inputs into a particular function or relation. It works for relations as well. Now you're going to run your domain values through some rule to get a corresponding output value in the y position, and then these are x, y pairs that you can plot. So for example, if I wanted a function rule that said triple the input, well first of all I need some inputs. So I'm going to choose some domains. I'm just picking anything. If my rule is triple the input, what do I get as my output? Triple this. Triple this. Triple this.
15, 20.
Alright? And then you can graph this. So this would be like an ordered pair. So you go right 2 up 6. You would go right 3 up 9. Go up, right? And so this is graphing the points that are created. Let's try another example of a function rule. If I have a rule that says your y value is 5 times your x value plus 1. And so we need some inputs. I'm just going to make some up. Okay, so 1. You put the 1 in here. 5 times 1. 5 times 1. 5 plus 1.
6.
Now you put a 2 in here, right? That's my new x. 5 times 2
10
plus 1.
11.
5 times 3. 15 plus 1, right? 5 times 4 is 20 plus 1. 5 times 26. Then you would plot these points. And one more rule. Now, whoops, that's the wrong thing. I should have put that. So this one says d equals 3t minus 4. Yeah, what's that? It's not saying x and y anymore. What do you think's going on here? It's using different variables. If I'm telling you this one's time and this one's distance, who's going to be independent and who's going to be dependent? Yeah, what do you think, Rand? Time would be independent, because it always is, and distance would be dependent. So then where does the time go? Is that an input or an output? Independents are inputs. So where does this one go? T is an input, and your distance, right? Your independent is time. It's going to go click away. Your distance depends on it. So if you're going 1 second, 2 seconds, 3 seconds, right? If it's 3 minus 4, uh-oh, I go negative. 6 minus 4, 9 minus 4, 12 minus 4, 15 minus 4. That's how we use these little function tables and then we graph them. So is this something you have seen before?
Yes.
Yeah.
Raise your hand if you have. Raise your hand if like, no, I've never seen this. This is the first time that that's happened. Last year nobody has seen it. Nobody. So that's good. Okay. So that means we should be able to graph this function y equals x plus 2. Now they have to tell you what the domain is. Remember what this is? What's domain? Set of inputs. So what do we do here? We make our little t table or our function table. We put our domain entries in. Our rule is y equals x plus 2. You might want to move over so you can see it better. So if my input is 0, my x is 0, what's my y value? Plug it in. What do you get? 2. This one says your x is now 2. 4. This one says your x is now 5. This one says your x is now 7. And this one says x is now 8. So now, what is your range? What's the range?
2, 4, 7, 8, 9, 10.
Well, why is that the range? Because what is range?
Yeah.
Set of outputs. So if you're given a domain like this with like numbers, and they give you a rule, how do you find the range? Plug each one of them in and get its value, you found the range. So now you plug these points into the graph. So 0, 2, don't go left or right, but go up 2. Go to 1, 2 to the right, and up 4. All right, you all know where we're in? We're all like filling this in on your graph? Bottom of page 2? We're all doing it?
Yes.
Oh, everybody's doing it. All right. 1, 2, 3, 4, 5. 1, 2, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now I go all the way to 9. Here, well, that's 7, 8, 9. And then, let's see, this is 8, and it's going to go up to 10. Okay. And now I have graphed this particular relation. Is this relation a function? Is it? Why? No, that's not a reason. Why? Go ahead.
Because all inputs only have one output.
Every input has one and only one output. Excellent. What's my independent variable here? Which one's independent? Which one's dependent? Who's independent? Who's dependent? Remember, the independents are your inputs. So which is my independent variable? What you have two variables. You have an x and you have a y. And which one is your independent variable? X. Which is your dependent variable? Y. All I'm looking for here. Okay, that's all we do.